Okay, so first things first. So you got the two sheets here. This is on line 2. You guys can add these to the wiki too if you want to. But here are the 4 kinematics equations. We've talked about 3 of those, but we haven't gotten to the 4th one yet, right? So let's look at how we can come up with this 4th one. So what if we were to combine sort of the definition of average velocity with the first 2 equations, right? So if we take the first kinematics equation, it just looks like this. Let's write it in terms of, notice that there's, along the left side, there's going to be the kinematics equation in terms of final position and initial position, and then on the right, we write it in terms of displacement, right? X minus X naught. So let's write it that way. So displacement equals average velocity, average velocity times time. So we're going to take that equation, and we're going to take this guy, the second equation, which is, we're going to use this one, we use this guy, V equals V naught plus A T. Okay, so we want to come up with an equation, the 4th one, which is kind of a unique equation because what do you notice if you scan down those first, or 4 kinematics equations? How is the last one different than the top 3? And, I mean, in many ways, but there's one really significant way. Okay, sure, but there's something missing from the 4th one that shows up in all the others. Time, yeah. The 4th one doesn't involve a t. So that's crucial. That'll be important as you start doing these problems. So then if we want to eliminate a t, we're just going to solve by substitution, right? So let's isolate t in this first equation. What is t equal to? If I divide both sides here, I just end up with t equals delta x over v bar, right? But what is v bar? Average velocity. So what is that? What's the definition of v bar? It's going to be the sum, right? So average is just going to be, it's the average of initial and final, right? So it's just going to be final velocity plus initial velocity divided by 2. Everybody agree? That's what this whole thing right here, that's just v bar, right? So then if I flip and multiply by the bottom, that puts the 2 on top, doesn't it? Right? So we end up with the equation t equals 2 delta x over v plus v naught. Okay, that's our substitution equation. Well, what if we substitute that in up there? Okay, what do we get? So then we end up with v equals v naught plus a times t, which is this stuff, right? A times 2 delta x over v plus v naught. Okay? Let's subtract v naught over to this side. So we're going to get v minus v naught equals, and let's just combine this. We're just going to get 2 times a times delta x over v plus v naught. Okay? You don't have to do this every time. We're just going to derive the equation, derive the kinematics equation, then you can just use it. What could I maybe do here? Multiply by what? Okay, good. We'll multiply both sides by the denominator, right? So we'll multiply each side through by v plus v naught. Right? So those factors cancel, right? Now, what do we get on the left side? That's a conjugate pattern, right? Going back to algebra 2, if we multiply something of the form a plus b times a minus b, what do we always get?
A squared minus b squared.
Okay, difference of squares. Good. we get a squared minus b squared, right? So our a is a v and our b is a v naught. So then we end up with v squared, and, okay. Are these vectors? I don't want to talk about that. Not really, because you can't really multiply vectors like this. So these are magnitudes. Okay. The reasons why I'm going to come back and talk about in more detail later in the class when it fits in with what we're doing in calculus. It's not important in terms of being able to do the physics, but when we do a product like this, we lose some of the vector nature of these things. But the magnitude still works for magnitudes, for speeds. So we get v squared minus v naught squared equals 2a delta x. Okay, that's an important equation. The way they write it in, yeah, that's the way I wrote it in here. I think in the book maybe they put the v naught squared on this side. I like it better this way. Okay. So there's our fourth kinematics equation. Okay? So we can add that to our list. Now we've got 4 equations. And so what we want to do now that we've got our 4 equations is we want to use them to tackle some situations, right? Answer some physics problems. So this leads us into the other handout. Okay, this is right out of the online textbook. But I sort of like the way they did this. So kinematics problem steps. They break it down into 6 steps. I've always broken it down into fewer steps in the past than this. I think some of these combine pretty naturally, but this seems reasonable. This isn't always going to work exactly in this order, but it's a good general strategy. So what does this say? Each of these situations, we want to examine the situation to determine which physical principles are involved. Well, this is all going to be kinematics. It often helps to draw a simple sketch. And it doesn't need to be a fancy sketch involving like pictures of boats and things. Really what we want is we want to represent the motion with vectors a lot of times. Okay? So we need to determine which direction is positive, which direction the thing is moving. And if they don't specify that, we'll pick the convenient way. Okay? Or a convenient way, and we'll just stick with it. So what else here? Once we've identified the physical principles, it's much easier to find and apply the equations. Okay, we're getting there. That's really it. So this first one is we're going to examine the situation, draw a picture, try to represent the information that's given to us. How might that look? Airplane lands with an initial velocity of 70 meters per second and then decelerates at 1.5 meters per second squared for 40 seconds. What's its final velocity? So what's going on here? What direction should we say the plane's moving? Right. To the right. Let's make it moving in the positive direction. How about, right? So we could represent, for example, we could represent the initial velocity like that, right? So that's v naught, and what's it equal to? 70.0 meters per second. Okay. What else is given to us here? What about this part? Decelerates at a rate of 1.5 meters per second squared. So we want to maybe attach a vector to that. What direction is the acceleration pointing? Okay, deceleration means slowing down. And if it's traveling to the right and slowing down, then the acceleration vector must be pointing that way, right? So what's our acceleration equal to then? Negative, because it's pointing in the negative direction, right? Negative 1.50 standard units, meters per second squared. And you could maybe even leave the units off. I'm going to put them on here at least initially. And then the other thing is they give us a time, right? And they want to know what its final velocity is, right? So we're also looking for, they're telling us t equals 40.0 seconds, right? And so if you wanted to you don't have to draw this, but if you wanted to sort of represent this as something changing in time, we've got this initial velocity vector, and then sometime later, we've got this slower final velocity vector, and that's what we're trying to find, right? Okay, does that make sense? Is that the only way to do it? No. It's a pretty good way to do it, though, because it gives us some, if you use vectors, it kind of gives you an idea about the directionality of this thing, right? Okay, so now, what about step 2? Make a list of what can be inferred from the problem. So what are our knowns and our unknowns here? Well, it's all pretty much covered there, isn't it? Initial velocity they gave to us. So if we want to make a list, I guess if we want to make a list of everything we know, initial velocity is positive 70 standard units. Acceleration is negative 1.50 standard units. Time is 40.0 standard units, and we're looking for final velocity, which we usually just write as v. Okay? So there's what we know. That combines steps 2 and 3. What are we given? And step 3 is what are we trying to find? Step 4, we're going to go equation hunting. We want to find the right equation for the job here. Ideally, we'd like to find a single equation that involves all 4 of those quantities. So which one fits the bill? Equation 2. Good. Okay, so we could go to the equation V naught equals, or sorry, V. V equals V naught plus AT. What is it that we're trying to find?
V.
V. That's what we want isolated. It's already isolated, right? So once we've isolated the quantity that we're trying to find, then we'll plug and chug. I strongly encourage you to don't plug in the numbers until you've isolated the variables. Numbers are messy. Variables are clean. It's nice and neat, right? So now we would just plug in this stuff and see what we get numerically. So this is going to be 70.0 standard units plus negative 1.50 standard units times 40. And then we just throw that in the calculator and see what we get. Throw that in the calculator and see what we get. Where's my calculator? There it is. Okay, the other thing I would encourage you to do is to, when you're doing calculations, use a graphing calculator method where you're doing everything at once. It's more efficient, right? So I would put all this in one entry, right? So this is going to look like, just like it looks on the screen, on the board. 70 plus, so plus and negative is minus, right? So minus 1.5 times 40 is 10. Okay? What are my units going to be? If I've used all standard units and I'm solving for a velocity, what's that mean? What units? Meters per second. Good. Okay, so we end up with V final equals 10. Is it 10 though? 10.0. How many sig figs do I have? 3. Right? 3, 3, 3, 3. Oh, I guess that's already included there. And we're doing a combination of addition and multiplication, right? We're multiplying measurements here, measured values, and so we have to only keep the smallest number of sig figs of any of the measurements, which is 3. So 10.0 meters per second. Okay, last step is that reasonable? You know, because a lot of times in physics, I mean, what if you got an answer of like 1,000? Well, that's not reasonable, right? That doesn't make any sense. You wouldn't start at 70 and decelerate and then end up with a speed of 1,000, right, or velocity of 1,000. 10 makes sense, though, doesn't it? Seems reasonable, right? So that's it. Okay. Here's in the book. Here's what they did. pretty similar to what we did, right? That's in the online book, though. You can look at that. Okay. Let's try another one. Maybe. There we go. Okay, try this. Take a second, see if you can set this up, work with your neighbor, that's fine. See if you can set up kind of a pictorial representation, maybe throw some vectors in there. Write down everything that's given, even if it's just implied. Identify what you're trying to find. Pick an equation that's going to work. Isolate the variable that you're trying to solve for and plug and chug. Let's pause for a second, just make sure we're all kind of at the same place after step one. How about? So suggestions now. I kind of ran you through the first one. Now you guys run me through this one. What do I, tell me what to write.
Acceleration equals 26.0 meters per second.
Okay, so what direction is it moving?
Right.
To the right, okay, good. So how am I going to represent the acceleration then?
Right.
Okay, vector going to the right. And it's 26.0 meters per second squared. Good. Something else. Times 5.56 seconds. Good. Okay. Okay.
Initial velocity is 0.
Initial velocity is 0. Okay, so what's, as a vector, that just looks like a point, doesn't it? Right. What's that mean if the initial, well, that comes from where in this? Starts from rest, right? So it's implied that the initial velocity is 0, okay? So V naught equals 0. And what are we trying to find?
How far it travels.
Yeah, how far it travels. And so if you want, it's kind of optional, but if you wanted to kind of try to write some kind of a diagram that represents the movie we're looking at here, it's starting off at rest, and sometime later it's traveling, let's see, so we don't know final velocity, do we? Okay, we don't know final velocity, so we're just trying to figure out, as it accelerates, where is it going to be, how far is it travel after our 5.56 seconds, right? Does that make sense? Okay, there's a bunch of ways we could do this. Let's try to pick the most efficient. We could do this with multiple equations, but given what we have up here, we have three things, don't we? We're given acceleration is positive 26.0, right? I should have put an 8 up there, huh? We have initial velocity is 0, and we have time equals 5.56. And what are we trying to find? Okay, distance traveled, so that means, not really distance in this case, displacement. So what's the equation that's going to fit the bill there? Equation 3. Right? Does that make sense? Okay. Equation 3 is the one that tells us if we write it in terms of displacement, displacement equals V naught T plus 1/2 A T squared, right? That make sense? What are we trying to solve for? Displacement, already isolated, so all I have to do is plug and chug. Is there anything that's going to happen that's sort of important about this equation here? Does it simplify? Initial velocity is 0, so that tells us that this term right there goes away, right? So really all we need is just delta x equals 1/2 AT squared. So now we can plug and chug. A equals 26.0 standard units. T is 5.56, and that's being squared. Throw it in the calculator, see what we get. Okay, so what do we get here? 0.5 times 26 times 5.56 squared is 401 point blah, blah, blah. How many sig figs can I keep?
3.
I can keep 3. What about the 0? Is that just 1?
It's not a measured.
Oh, it's not measured. Good. So that's as many as we need, right? It's exactly 0. So we can keep 3, so that rounds back to what then?
400. 402.
402. Good. And what are my standard units for displacement? Meters. Okay, so $402 meters. Is that reasonable? Did I not add correctly? What did I forget? Oh, you were thinking about that term right there?
Yeah, it's so down.
Okay, does that seem reasonable? Dragster's huge acceleration. How many G's is that?
A lot.
A lot.
Close to
I mean,
three.
what is the, do you know what the acceleration of gravity is? 9.8, yeah, good. So roughly 10. So that's, I mean, that's like pushing 3 Gs, right? That's a lot of acceleration. So for 5.56 seconds, yeah, you would be going pretty fast at the end of that, wouldn't you? Okay. All right. Okay, I included there's what they did. You know, real similar to what we did. You can look at that if you want to. Okay, another one. This is a little better question. I like this. So, on dry concrete, a car can decelerate at a rate of 7 meters per second squared, whereas on wet concrete, it can decelerate at only 5 meters per second squared. Find the distances necessary to stop a car moving at 30 meters per second on dry concrete and on wet concrete. And then, let's just do part C. Part C is a good question. Find the displacement from the point where the driver sees a traffic light turn red, taking into account his reaction time of 0.5 seconds to get his foot on the brake. Okay. So rather than do all this stuff, how about if we just do on wet concrete, how much distance does it take for the car to come to a stop? So what's displacement? So we're just going to do, how about if we just do this one? Find displacement for wet concrete. Okay.
Were you including the reaction time?
No, we're going to include the reaction time, because that's something important going on there. What do you think? Before we even start this thing, we got to organize the way we're going to approach this. What can you tell me about the suggestions? The motion of the car. How can we describe the motion of the car? How many stories are being told here? There's 2 in a way, aren't there? Right? What do I mean by that? Okay, wet and dry, but what if we're even just talking about the wet part? If we've got a car, we're only going to consider the car driving along on wet concrete, and we want to know what the total displacement is from the time the driver sees the red light. Okay. It takes half a second to hit the brake, and then once the driver hits the brake, we have all the information up there, right? Why in a way, are there two separate stories there?
There's a time between when he sees the light and when he hits the brake, and
Okay.
there's a time between when he hits the brake and stops.
Okay, do you see that those are two problems in one? Because the situation changes, right? We can't use the acceleration of, well, it could be, what, -7? That's not happening when he's coasting along before his foot hits the brake, right? What's the acceleration there during the first half a second?
0.
0. Yeah, it's just traveling along at constant speed, right? That's implied. It's moving along at a certain speed, right? That make sense? So for half a second, it's just coasting along, and then he hits the brake. Okay, so what distinguishes the motion from the first part, call it part A, to the second part, call it part B? What's changed? Acceleration has changed. And that's kind of a rule in physics. When the acceleration changes, you have to change, you have to start a new story, right? It's like a subproblem within a problem. So we'd have to break this into two parts. First part's pretty easy, right? Part A, what are the conditions for part A? We won't even draw a picture. What do we got for part A?
Then there's
Per second or half a second.
Okay, so we're going at 30 meters per second. So that's the initial velocity, right? But it's also the final velocity, isn't it? Right? So V naught equals V equals 30.0 meters per second. Okay? And then the only other thing we know is the time, isn't it? Right? We know that T equals 0.500 seconds. What are we trying to find? Okay, displacement, right, for part A. So we're trying to find, we'll call it delta x sub A for part A. Okay, so which equation is going to fit the bill there? Ah, 1. Now let's think about number 1, equation number 1. Equation number 1 is delta x equals v bar times t. Well, I don't see a v bar there. Well, what about, how come v bar works? That's average velocity.
Velocity doesn't change.
Doesn't change. So the average stays the same the whole time. So this is actually either one of those two we could consider to be v bar, couldn't we? Right? Does that make sense? And so this is a pretty easy one then. We're trying to solve for delta x, so we can just plug and chug. We end up with 30.0 times 0.5, which is what? You can tell me, I've got to do it. 15. Good, so delta x sub A for the first part is 15.0 meters, agreed? Okay, make sense? Now we got to move on to part B. Okay, what about part B? Let's write down, before I scoot down here, let's summarize everything that we know about part B. What's my initial velocity? 30, okay. What else?
Acceleration is 5.
Is 5?
Negative.
Yeah.
Negative. It's got to be negative because I'm slowing down, right? If we're assuming that my initial velocity is to the right, which is convenient, right, then acceleration must be to the left. So acceleration is negative 5.00 meters per second squared. What else?
VF
Velocity
is
is 0.
Okay, final velocity is 0 because it comes to rest. That's implied, isn't it? Okay. So final velocity is 0, and what are we trying to find?
displacement.
Displacement. Okay, well, which equation fits there? Four. That's That's our new one, isn't it? There's no t, right? Okay, so we got to use equation 4. So that's the one where we've got final speed squared minus initial speed squared equals 2a delta x. What are we trying to solve for? Delta x. So what do we have to do to get delta x by itself? Divide both sides by 2a. Okay, so that gives us the equation delta x equals v squared minus v naught squared over 2a. So let's plug and check. What's my final velocity? 0. So that goes away. So I get negative. Now, I'm not squaring negative 30. I'm squaring 30, right? I get negative 30 squared, 30.0, wasn't it? Divided by 2 times, what's my acceleration? Negative 5, okay? So what's that give me? 30 squared is 900. So I get negative 900 on the top. Standard units. 2 times negative 5 is negative 10. What's negative 900 over negative 10? 90. And 0.0, right? We get 3 sig figs. So we get delta x of b is 90 meters. We got 15 meters for delta x of a, so what's the total? 105. Okay, make sense? Kind of seeing how, and this is just how they all work, right? Now eventually, you know, this is sort of introductory. Where do we go from here? Well, we're going to talk about free fall motion at the end of this section, and then we'll be done with this unit. You know, we'll kind of put it all together, take a little test. Then we're going to go on in the future. We're going to look at how we can work towards doing kinematics in 2 dimensions. Okay, but to get there, we have to be able to deal with vectors that are not pointing in a straight line. So we got to kind of take a little time out, and we're going to talk about the math of combining vectors, you know, that are pointing at right angles or maybe not at right angles. How do we deal with that? We got a pretty simple, efficient way of handling that we got to come to grips with. And then we can take all the stuff we're doing here and we can apply it to more interesting problems where the motion is not just in a line. It can be in 2 dimensions instead, right? But looking down that, you know, down that pipeline towards where we're going, this essentially is going to be the same stuff we're going to end up doing when the problems get much more complicated, right? So getting used to using these equations is important. Okay? So you get a little practice with that. When are we out of here?
8 minutes.
8 minutes. Okay. Maybe we got time. Can't remember if I have. Yeah. How about this one? So you guys just try this one on your own here. I won't even. I'm just going to shut up and get out of the way. Whoops. You try that one.